Okay, everybody, what we're looking at now is the graph of the derivative function. When we're sketching derivative graphs, this is something that comes up quite commonly on the exam. What we're doing is that we're changing the nature of our axes. So we are going to have new axes set up where we still have our x values on the horizontal axis, and instead of having y on the vertical axis like we used to, instead this axis is going to show the value of the gradient for the different values of x. So these are going to be derivative graphs. Now a few points to note. The derivative does not exist at these particular points, and we can think about why that might happen. If we had, so I'll just draw some axes here. If we had a particular function, so this is my original function that I'm drawing, so I've got my normal xy axis, and say I had a function like so. It has a sharp turn there, and a, whoops, sorry everyone, having a little trouble drawing here. And we have a discontinuous point here, and we've got our end point here. Okay, if we had a function like this and we're thinking about what happens, remember when we're finding the gradient of a point, that means we're also considering essentially the gradient of a tangent at that point. If I'm thinking of my endpoint here, if I'm trying to draw a tangent, there are multiple possible tangents. There's not just one tangent, there are multiple lines that we can draw that touch this curve in only one point. So therefore it is not possible to come up with a gradient at this endpoint. The same thing happens at our sharp turn. We can draw a tangent, and let's just pretend that these lines are straight, because I am having some issues here. But we could draw a number of different potential straight lines, all of which are touching this sharp curve point at one point. So once again, we're not able to come up with a value for the gradient. We can't draw a unique tangent. So for all of these, we get no unique tangent. And therefore, the derivative is not defined at that point. Again, same thing at a point of discontinuity here. We can have a tangent here, we can have one there. There's not going to be any continuity there. The derivative does not exist at these points, so therefore we cannot show it in our derivative graph. Now I might just make myself a little bit of space here so we can consider the next options. So let me just get rid of this here. Okay, and we'll see our curve again. Okay, so if we have our original point here and we had a function like so. If on our original graph we have a gradient of 0, so at this point here we have a gradient of 0. So that means that this, let's say this x value was -1. At the point here at -1, the gradient is 0. So if I'm looking at the gradient here, this would be a gradient of 1, a gradient of 2, and so on. This point here, we have a gradient of 0. So therefore we have an x-intercept at this point. If the gradient is greater than 0, so in my initial graph we have got a gradient greater than 0 occurring, that means a positive gradient, so an upward slope. We've got it happening in this section of the graph and in this section. I might say that this is occurring at 1 as well, just for the sake of argument. Gradient is greater than 0, that means the curve is above the x-axis. Gradient greater than 0, that means I'm going to have a section above. I'm going to be drawing this somewhere above the x-axis, because here's my dy dx. We've got a positive gradient here, so I need +1 or +2. If the gradient is less than 0, so when we're looking less than 0, Therefore, we've got a negative gradient, so this is this section of my original function here. I'm going to be getting the curve below the x-axis, because below here we would have negative gradient values, so I would have a value below. Now this one, if we can calculate the exact gradient, we must do so. This is generally when we've got a linear section of the original. And we'll do an example showing this a little bit later on. Quite often we're not able to actually calculate the value of the gradient. If we know the shape of the original, we can use it to find the shape of the derivative. Okay, so if our original function is a positive quartic, when I differentiate this function, it would then become a positive cubic. So if my original is a positive quartic, my derivative graph would be a positive cubic. Similarly, up in my example here, this original is a positive cubic graph. We know that because it's a cubic, because it has 1, 2, 3 branches, and it's positive because it ends sloping upwards. If my original function was a positive cubic, that means that my derivative function, if I differentiate a cubic, so if I'm differentiating x cubed, I would multiply by the 3, multiply by the power, subtract 1 from the power. My new function will be a positive quadratic. And this makes sense of the things we were talking about before. We had our section of the graph, our positive values above. It's going to be a positive cubic. Let's say this is the point 1, sorry, at 1 and at negative 1. So if we're comparing to our original graph, what we had here, in the original we had a 0 gradient at negative 1 and at 1. So here's our gradient. A 0 gradient occurs along the x-axis, and we had a 0 gradient at negative 1 and at 1. In our original here, we had a positive gradient where x is less than negative 1 and where x is greater than positive 1. So that a positive gradient means we needed a gradient above the x-axis. Both of these sections here are giving us a positive gradient, a gradient above the x-axis. You had a negative gradient here, so it's below. Okay, let's look at a specific example. So we consider our original, in this case we've got 1, 2, 3 branches, it's sloping up. So our original is a positive cubic graph. That means that my new function, my derivative graph, would become a positive quadratic. If I differentiate x cubed, I'd get 3x squared. Now we draw our axes. Okay. Once again, like I've said before, when you draw your axes, you should be using a ruler. Okay. Now, instead of a y-axis, this becomes the derivative axis, dy dx. Our key points are happening at negative 1 and at 2. So what we're looking at here, okay, we had a we have a positive gradient, then we have another positive gradient occurring here. So a positive gradient and a positive gradient. So that means we need to be above the x-axis here and above the x-axis here. In between these two sections, so this section down here, we've got a negative gradient. It needs to be below the x-axis. It becomes a quadratic graph. So our graph is simply going to have a quadratic shape, and it's going to look like so. I'll just get rid of this little extra bit that we had from earlier on. Okay. And we've got our new derivative graph. Now we are not able to actually calculate any of the other features. Okay, we can't figure out exactly the values of these, but that's okay. We don't need to. We don't need to calculate the value of the new stationary points. We just need to get the general shape and a general idea of what it looks like. Let's do another example. Okay, so we've got our second example that we're looking at here. So we do the same thing again. We think about, for our original function, what is the shape of our original function? Now, our original one here is, we have, let's think about this carefully now. We've got to be careful. We've got 1 branch, 2, 3, the stationary point of inflection counts as a branch, 4. We've got 4 branches there, and it ends sloping upwards. So this function is a positive quartic, which means it's going to become, in our derivative graph, a positive cubic. Let's think about our stationary points. So where does the gradient equal 0? So where does our gradient equal 0? Where does dy dx equal 0? It occurs at the values of x equals 1 and x equals 3. So we're looking for our stationary points. We've got one occurring here and another stationary point occurring here. This 2, an x-intercept, that's not a stationary point. So when we're sketching our derivative graph, once again we have our axes. We need to make sure that we label our axes, and we need to make sure that our vertical axis is labelled as dy dx. So this intercept here isn't given, but that's not relevant. That doesn't help us sketch this graph. We had a point here at 1, that's going to be an x-intercept because the gradient is equal to 0. Remember, the y-axis shows the gradient. We have another point here at 3. When we're thinking about what's happening here, let's now consider the shape of our gradient. So I might just even draw a quick little sketch here before we get our final graph, just to get an idea of what our shape will look like. Okay, so we have our first section is a negative gradient. It's sloping down. That means what we're going to have here, less than 1, we're going to have a part that's below the axis. In between the points 1 and 3, we have a positive gradient. It's sloping upwards. So in between 1 and 3, it needs to be a positive gradient. At 3, we've got our 0. At 1, we've got 0. And when x is greater than 3, it's again positive. It's again sloping up. So we need to make a x cubed shape. If we think of our sine diagrams that we did earlier, our sine diagram, that's not how we draw a sine diagram, is it? So our sine diagram would have a negative part, a 0, a positive, 0, positive. So the shape of our diagram, it's going to be below the axis at the point where x is 1, so negative means it's below the axis, 0, now it's going to go above the axis, but remember it has to be 0 again at 3, so we're going to have a turning point back here. We have 0 at 3, the gradient is still positive, so that means we are above the x-axis. And this is our positive cubic graph that we were looking at. Notice that it doesn't matter what the gradient is of each of the different sections in this derivative graph. Okay, it doesn't matter what the actual gradient of these lines are. What does matter is where the graph is above the axis and where the graph is below. Okay, so this graph is a bit of a different one to what we were looking at before because it's actually a hybrid function. We've got two different sections. In our first section here, it's linear, and we have actually 2 points. We know the value of this point here, which would be 0, 4, and we know the value of this point here. So therefore it's going to be possible to calculate the actual gradient there. The second part of our hybrid function looks like it might be quadratic. So if this looks like it's part of a quadratic graph, then our derivative graph will have a linear part there. So let's think this through. Let's actually work out the value of our different parts. So we know how to work out the value of a gradient for a linear line. We've got our 2 points here, 0, 4, and the coordinates of this second point would be 2, 2. Remember, to work out the gradient of a straight line, this is not news to you. We've got our gradient formula that we can see here. So we'll have our y2 value 2 minus y1, which is 4, over x2 minus x1. So we get a value of negative 2 over 2, or a gradient of negative 1. So we can actually sketch this. If we draw our axes, okay, we've got our x value and our derivative value. We actually know that at negative 1, in between where x is 0 and where x is 2, we are going to have a gradient of negative 1. So we can draw that like so. Remember earlier we mentioned that when we have either endpoints or sharp turns, the derivative is not defined. If we need the derivative curve to not be defined, for a curve to not be defined at a point, you might recall what we do is that we draw an open circle. So we're going to have open circles at those two ends there and there. We then think about our next part. This section of our curve here that we're looking at here, it has a negative x squared shape. Negative because it ends pointing downwards, and x squared, it looks quadratic. If I was to differentiate this, it means that I will get a negative x shape. I'll get a linear shape that's sloping downwards. So we know it's going to be linear, we know it's going to be sloping downwards. So linear sloping downwards, it's going to be going downwards like so. Looking at the original, we have a positive gradient here, so it will have to be above the x-axis between 2 and 3. We have a value of 0, a 0 gradient at x equals 3, so we'll have an x-intercept here on our derivative graph at 3. And between 3 and 5, we've got a negative gradient. It's sloping downwards, so it's going to slope downwards between 3 and 5. So we can show that. We're going to start at 2, we're going to slope downwards, start at 2, slope downwards, pass through x is 3 and continue down. Let's pretend that was straight because I am having some issues. Down to 5. Once again, these points are not included because in the original graph we had a sharp turn at 2, which is not included. We had an endpoint at 5 in which the gradient is also not defined. So this is the best we can do. We are not able to actually figure out at which value this occurs or at the y value of our endpoint here, at either of the endpoints. We don't have enough information, so we can't label them. You could have drawn it in a different way as well. We don't know how far down they're going. So there could have been quite a few different answers. The main points that we do need to show is that there is an open circle at x equals 2,